Okay, here's yet another example where we're looking at getting all of the relevant features of a function by using some computing tools. So in this case, again, I have not shown you what the function is, but I've shown you the default view graph in Desmos. And every technology is going to have a different default view. There are decisions that are made in the programming of that technology. In Desmos, the default view seems to be where the x-axis goes from -10 to 10, and then the y-axis is whatever is shown for that size of window, so that the x and this y scale are the same. So this is the view of this particular function, and the first thing I'm going to do before even looking at the function is I'm going to poke around and see what I'm missing. It looks like there's a whole chunk of graph missing here, so I want to zoom out and see what's happening here. Ooh, oh, there's something happening up here. So that is interesting. It looks like I have a local minimum here at x equals about 2.5. So let's take that and it looks like the limits at infinity appear to be maybe 0. If I trace around here, it looks like the y coordinates are getting closer and closer to 0 as x gets larger. It looks like I have some numbers excluded from the domain, maybe around, I don't know what. If I zoom out again, looks like maybe around x equals 2, I don't know, and maybe around x equals 5. So I found some information there. Let's see if we can get an idea of what this function is doing by looking at the function itself. Okay, we have a rational function again. So we can dive right in with the domain. We do have an exclusion from the domain at x equals 2 and an exclusion at x equals 4 because 2 and 4 would both make the denominator 0. Other than that, there's no exclusions from the domain. So we could say all real numbers except 2 and 4. Or another way of saying it is in interval notation, so -infinity to 2. I don't have a union. Oh, how about if I just use a u? Okay. Union from 2 to 4. Union from 4 to infinity. Oops, that's not the right symbol. Okay. There's my domain. The range, it looks like all real numbers greater than 0. Let's see. It does look like in fact, it looks like all real numbers greater than or equal to 0. It's hard to say. So as it looks like for all, looks like we do actually have an x-intercept at x equals -1. So there's something interesting happening here. I'm gonna say this though. It looks like all real numbers greater than 0, and I just noticed this like x equals -1 intercept, and it does look like the y values get negative. So something else is going on here too. Okay, but I'm just going to put this, it looks like y is greater than or equal to 0. Or y is greater than or equal to some small negative number. Okay. Symmetry and periodicity. This one's pretty easy. We have, there's no periodicity periodicity, we don't have any trig functions in here. And the symmetry, it doesn't look like we have any. And I am going to confirm that with evaluating the function on two symmetric inputs. So f3 of, and I don't know, -1 and f3 of +1. These outputs are neither the same nor are they opposites of each other, so that takes away the even-odd symmetry. Periodicity is taken away by the fact that there is no trig functions. All right, intercepts. So it looks like we have an intercept at x equals -1. So x-intercept at x equals -1, y-intercept actually at x equals 0. If x equals 0, then y equals 0 as well. And then the x-intercepts, that's going to give us one x-intercept, and then -1 is going to give us a y-intercept, or sorry, an x-intercept. So let me, it's going to be 0, 0, and -1, 0. Okay, those are the two intercepts. And if this is kind of interesting, that actually tells me if those are intercepts and what is happening here. Y is positive to the right of 0 and positive to the left of 0. That makes sense because this is in fact a double root. Okay, since I have an x squared there, it's a double root, so I'm going to be kind of touching this way. X equals -1 is a triple root. That means it looks a little bit like a cubic around x equals -1, which means I should be dipping below the x-axis. And I do, but we don't, it only comes a little bit below. So again, we're gonna go along and see what other information we get here. But the numerator basically tells me all that I need to know about the intercepts, along with the fact that, you know, we have to use the y-intercept is where x equals 0, and that happens to also be one of the x-intercepts. Okay, so those are the only two intercepts. End behavior. Okay, it looks like from the graph, it looks like the limit is 0. Let's go back and look at the function. So that numerator is a degree 5. We have a second degree times a third degree is a degree 5. The denominator is degree 6. I have degree 2 times degree 4 is degree 6. So if a degree 5 polynomial divided by a degree 6 polynomial is going to go to 0 as x goes to infinity, or positive or negative infinity. So y goes to 0 as x goes to cute, plus or minus infinity. Okay. And, you know, if you want, you can double check, confirm that using Wolfram Alpha. I'm going to copy this and go to Wolfram Alpha and take the limit of that as x goes to infinity. Double check that it's doing the right thing. That looks like the same function. As x goes to infinity, it is, the whole thing goes to 0. And also as x goes to negative infinity, let's confirm that. Should be the same. All right. Just confirming the things that we should already know here. I also wanted the limits around edge of the domain. So we want the limit as x approaches, what is it? As x approaches 2 and as x approaches 4. So let's go back here as x approaches 2. And technically we should probably separate it into approaching 2 from the right and approaching 2 from the left. Since Wolfram alpha says that this limit as x approaches 2 is well defined as infinity, that means that the left-hand limit and the right-hand limit are both infinity. And change this to as x approaches 4. And the limit as x approaches 4 is infinity. So let's actually put in x approaches 2 and as x approaches 4 are both infinity. Okay, and I want to put in those vertical asymptotes. I want to put in sorry, not with quotes, x equals 2 and 4, and I'm going to put those in as a green dashed line. And let's just say for y is positive, just for, I don't know, for aesthetics reasons. Okay. Intervals of increasing and decreasing. And this is a little bit hard to see because we have, you know, it looks like, so if I click on this function, it highlights 3 points here. Now these 2 points, -1, 0 and 0, 0, are both intercepts of the function. Those are 2 intercepts. So what is this thing? And kind of thinking about what happened, we saw that this function, the y values seem to be kind of positive. So let's actually, like, maybe we could zoom in. Can we zoom in? Oh, yeah, see, it's showing a y value that is actually positive here. So that means I have this like hidden local maximum there, which is kind of interesting. And so I think let's get a good picture of this by taking a look at the derivative. Okay, and again, with this function, I see this is a rational function. I am capable of calculating that derivative by hand. I do not want to. So I'm going to go to Wolfram alpha, and I am going to calculate the derivative. Before I use the word derivative of, that. And I want to also point out that, you know, we can use that notation d over dx of. So I'm going to do that. And make sure I close my parentheses. Okay. So there's the derivative. Interesting. All right. Let's take that. I wonder if it does not show the numerator as being factorable, that cubic. But that cubic, because it's a cubic, it has to have another 0 in it. So I want to copy and paste that. X times x plus 1 squared. Where am I? Let's see what we can. What is this? F3. So I'm a little concerned. There's something subtle going on here, that there's maybe a few different zeros and possibly some very shallow local maximum or minimum values. But yeah. So let me pull that up again. It is x times x plus 1 squared times x to the third power plus 18 minus 44 minus 16. So this is an x squared term. Double check. Yeah, okay. X minus 4 to the fifth, x minus 2 to the third. Okay, so 2 and 4 are still excluded from the domains of the derivative. And this gives us I got something wrong because this function is not showing the same as the red function. So what did I write wrong? X times x plus 1 squared, x minus 4 to the fifth, x minus 2 to the third, x cubed plus 18x. Ah, it's negative. There's a negative sign there. Okay. All right. So, turn this off. Make this orange for no apparent reason. So, we have, it looks like at least three roots, and I'm going to employ Wolfram Alpha to calculate roots of this for me, because Wolfram Alpha did not actually find the factor this number, which is a little bit, that means that probably the root is an ugly number. So I'm going to go back to Wolfram Alpha and find the roots of that polynomial. Okay, it gave me those roots in exact form. I'm going to ask for approximate forms. And it looks like there are 3 roots to that polynomial, which is a little bit frustrating. I want to go back to the exact forms, because in the exact forms it has i's in it. But that function we see, it shows 3 real roots. 3 real roots. Okay. And that is, I'm looking back here, this orange plot is not just that cubic, it's that cubic mixed in with a whole bunch of other stuff inside of a rational function. But that cubic itself has 3 real roots, which is good for us to see. I want to go back to the approximate forms. Okay, so there are 3 real roots to that cubic. Let's take that. So the first derivative has roots 0, so that comes from this factor here, -1, and this is going to be a double root. And then there are 3 real roots from that cubic. So I am going to take this, I'm going to ignore the exact form, and we're just going to take this to three decimal places. -20.145 and negative 0.322 and 2.467. Okay, so that's the three derivatives of, the three roots of the first derivative. All right. So the fact that this is a double root, this squaring, means that for x outside of -1, for x less than 1 and x greater than 1, the sign of the derivative is going to not change, okay? And you can see that basically because this term is squared, that factor does not contribute to the sign of the entire derivative. So, yeah. So we can kind of look and see, this is all much more subtle. So let's take this thing. I'm going to take this whole thing and I want to Wolfram alpha it. I want to see if it gives me a better plot. It doesn't give me really lovely plots. Okay, but we kind of see there's a root happening here. Yeah. Let's see what else it tells us. There's alternative forms, I don't care. Partial fractions, I don't care. Expanded forms, I don't really care. I want to know about roots. Here's the roots, which are the things that we found before. I kind of want to know where it's positive or negative. Okay. Okay, so that tells me I am going to order these roots in order. So -20 is going to go over here. Double root. The negative, that one is here. Okay, so these are the roots of the first derivative, and the thing I'm going to do is I'm going to use desmos to calculate the signs of these. And I do also want to pay attention to the fact that there's also a 2 and a 4 that can cause the sign of the derivative to change. So I'm not putting 2 in here as a root. I'm indicating this as a place where the sign might change. So places where the sign might change. Sign of the derivative. So let me just copy this back here. Here are the roots, not that, and take away the, okay, so those are the actual roots, and these are the places where the sign might change, and so I'm going to use this as a way for just calculating what is, like, whether the derivative is positive or negative outside and between these roots. So I'm going to take g of negative, anything to the left of -20, so let's say -30. So the first derivative must be negative for all numbers to the left of negative 20.7. So f prime of x is negative for x less than negative 20.145. Okay. And now I need a number that's between negative 20 and negative 1. So g of, I don't know, negative 10. And so that tells us that f prime of x is positive for x between negative 20.145 less than x less than negative 1. Okay. And so this says that if the first derivative is negative, that means that f is decreasing. And so, yeah, I'm in math mode, so Desmos sees sin and says, oh, that's the sine function. Okay, let me just do it that way. I'll abbreviate it. So in this interval, f is increasing. I'm going to expand this. Okay. And then what is it? Between negative 1 and negative 0.3, so g of negative 0.5. For example, that's positive. Again, this is where at negative 1, the sign of the derivative is not going to change because that's a double root. All right. So that is the same for, this is for x going from negative 1 to negative, what is that number? 0.322. And let's take g of, from negative 0.322 to 0. So negative 0.1, that is negative. So that means the first derivative is negative for x between negative 0.322 less than x less than 0. All right. And what's next after 0 is 2. From 0 to 2, it looks like the first derivative is positive. We can actually see that. So the first derivative is positive for x between 0 and 2. From 0 to 2. What's happening from 2 to 2.4? So let's do g of 2.2 is a negative number. It's a very large negative number. So that means it is decreasing here. So this is from x going from 2 to, what was that number again? 2.467. and it looks like maybe this is the G is crossing the x-axis. It looks like maybe in this direction, so it was negative and then becomes positive. Let's double check that by taking between 2.4 and 4, so let's take 3. Is a positive number, so that means the first derivative is positive for x between 2.467 and 4. So f is increasing, and for x greater than 4, it looks like the first derivative is negative. For x greater than 4. Okay, so that was more involved than I expected. But this does tell us that there are some interesting things happening here. It tells us, so it's first f is decreasing, and then we must hit a relative or local minimum, because then f increases and then it continues to increase, and then we must hit a local maximum because then it starts decreasing. We must hit a local minimum because we went from decreasing to increasing. And here we went from increasing to decreasing, but at x equals 2. So that means that is not actually local maximum or minimum. That's just that we have an asymptote there. X equals 2 is outside of our domain. But then we go from decreasing to increasing at x equals 2.4, which tells us that we went down and then up, so this must be a local minimum. And then at x equals 4, that is outside of our domain, so this just means that we were increasing going into 4 and decreasing coming out of 4, so that must mean that we have the limit as x approaches 4 must be infinity on both sides of 4. So that tells us something about the limits as that's something that we saw with the limit before. Okay, this was quite a bit. Okay. So let's put this again together. So this was for x less than negative 20, it's decreasing, and for x greater than negative 20, it's increasing. So we must come down and then up. We must have a local minimum at negative 20.145. So that must be a local minimum. Of negative 0.017 at x equals negative 20.145. Okay. Decreasing and then increasing, increasing and then increasing, increasing and then decreasing. So at x equals negative 0.322, I go from increasing to decreasing, so that must be a local maximum. Negative 0.322 is a local maximum. Whew. So that is a teensy number. This is why we couldn't see it on this graph. And this is why we need to use some calculus to find those little humps. Local max value at 0.00001717. That's 1718. At x equals negative 0.322. All right. So f is increasing and then decreasing at negative 0.322. And then it's decreasing and then increasing at x equals 0. So that tells us decreasing and then increasing, so x equals 0 must be a local minimum. So let's calculate what is g of 0, or sorry, f3 of 0 is 0, okay. So that was a local minimum value of 0 at x equals 0. And then from 0 to 2 is increasing, but then I have an asymptote, so then from 2 to 2.467, it's decreasing. That's coming off of the asymptote. And then here we have at 2.467, it switches from decreasing to increasing, so that must be a local minimum. So 2.467, we must have a local minimum. Local minimum value of 210.570 at x equals 2.467. All right. 2.467, and then going into 4, we're increasing, coming out of 4, we're decreasing, that's just the asymptote. Okay. This tells me a little bit that one of the things that I want to get out of this picture is I actually want to get a, I want to grab some snapshots that are kind of zoomed into some of these local mins and maxes. So, I mean, one of the things, you know, I can see this local minimum value of 210. This also tells me, like, where do I have local mins? It looks like this, this must be our absolute minimum value then, right? Because this is the function goes down, and then, like, you know, everything to the left of negative 20, the function is decreasing, which means that going backwards on the graph, meaning going more to the left, it would be increasing. So, and then it never gets below that again. So, this, let's say, and global. So that tells us that the y values go down as low as this number, negative 0.017. And it looks from the graph as though, let me get rid of this orange graph, I'm done with it. It looks like from the graph that I do actually cover all of the y values. So I can actually see that, where is my range? What is it again? This was at negative 20. Negative 0.017. So its y is greater than or equal to negative 0.017. Okay. Yeah, so, I mean, looking at this, I feel like I would, in order to really see that there is that local minimum there, I would want to stretch out the y-axis without necessarily stretching out the x-axis. And it's on the level of hundredths. So negative 0.02 to just to 0. Oops, sorry. That's not what I wanted. This is from like negative 25 to negative 15. The y value is negative 0.02 to 0. And then, you know, this is kind of zooming in on that teeny little bit of the graph, and now I can see that minimum y value. And if I zoom out, ooh, that really accentuates, and that it really accentuates that minimum value and shows it as a global minimum in a kind of interesting way. And look at the scale on the y-axis. It really is like, you know, this is negative 0.05. So it's a teensy-weensy y range compared to the x range here. Okay? And so that kind of zooms in on that piece. And maybe we want to zoom in on these pieces here, which are still kind of hidden. So we had a local minimum at x equals 0. You can kind of see that a little bit. And this one was a local maximum at 0.000017. And so, like, I can try to zoom in on, you know, the y-axis be 0 to 0. It was 12342. Okay, so now if I, you know, looking at zooming way into teensy y values, I can kind of see that hump being accentuated. And, you know, maybe let's try this a little bit more. So this is not negative 6.7, it's times 10 to the negative 6th. So let's take a step back from this. Yeah, let's just leave it at that. And so that gives a little bit more of a hump there and kind of accentuates that hump and shows the relative minimum there. And this is something that kind of shows you that there's no one picture that is going to show you all of the features of this graph. Like here's a view that gives us a picture of that particular feature. And, you know, if I zoom way out, like I'd have to zoom way out to get a picture of, you know, this relative minimum. But then we're also we're missing that one high one. It was like, what, 210 or something? The local minimum at 210. So we might want another picture of where x goes from, I don't know, 0 to 4 and y is somewhere around 210. Let's try that. Let's say y goes from 190 to 250. And so we can see that local minimum value there, right? That at x equals around 2.467, that we have a local minimum of 210.57. Okay, so that was a lot right there. And we can see, like, from all of these different viewpoints, we get a picture of the concavity as well. So it looks very much like the function is just going to be concave up between 2 and 4. I'm going to guess that. And it looks like it's going to be concave up to the right of 4. And it looks like it's going to be concave up between 0 and 2, I think. And this is where we had a little hump here. So somewhere in here, it's going to switch from being concave up to being concave down. So there's going to be probably 2 points of inflection between -1 and 0. And then this is where it kind of goes down and hits that relative minimum at -20. So it's going to be concave up for some amount of time there. So yeah, let's see. Where is our first derivative? What a ugly monster. Let's take the derivative of that. Or we could just go back to the Wolfram alpha and take the derivative of the derivative. And that is an ugly mess. It is a 7th degree polynomial. I wish there was a way to copy and paste that. Oh, copyable plain text. Okay. I think that this might... so this is the Wolfram language code. I think that this might not be available for the free version. Let me double check that real quick. Let's try... plain text. Oh, it is available. Wonderful. Okay, so let's take this part that is, oh, it just says copied. Okay, so let's take that and go back to desmos and see if we can put that in. Boop, 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 boop. Here we go. I'm going to put it in math mode. Wonderful. And I'm going to take all of this stuff out. Okay, and I'm going to put this is a fraction, there's that division. So I'm going to make this in fraction form. Divided by, oops. I believe that's right. Let's double check and look at y equals f3 double prime of x. And it looks like it's graphing the right thing. So it looks like I didn't screw anything up by copying and pasting it back. Okay, intervals of concave up and concave down. I have a 7th degree polynomial. What a mess. I'm going to ask Wolfram alpha to give me roots of that. I go to this roots thing, roots of this polynomial. There are 5 roots. And, all right. Oh, okay. So, -35.3113. So this is the second derivative. And I'm going to call this h of x equals that. Because I'm gonna do the same thing I did with the first derivative, where I ask it to evaluate the second derivative at some points between the places where the second derivative is 0. So second derivative is 0 at let's look at these. it's here, -1, -35.3113, -1, -35.3113, -4.97777, -0.5427, and -0.1084. Okay, I am going to put these in ascending order, so take that out and put it here. -4.9 is next. -1, -0.5, -0.1. Okay. So I am going to ask Desmos to calculate, and I can ask it to calculate h of these values between these, and I can also ask it to calculate f3 double prime of values. To the left of -35 would be -50. It's negative. So that says, is concave, it should be concave down, since the second derivative is negative to the left of -35. So x less than -35.3113. Now I need some number between -35 and -4.9, so I don't know, -20. And again, I can call this f3 double prime, or I can call it h. Either way is going to give me the same answer, hopefully. And I think in some ways maybe using f3 double prime, I don't know. I feel like I did check to see that I got the right h. So if I'm making a mistake in one of these, then I probably got a mistake in boundary points, so there's bigger problems. So that is positive, so that tells us that f is concave up for x between -35 and -4.9. Okay, so -35.3113 less than x less than -4.977. And then I want something between -4.9 and -1, so take f3 double prime of -2. That's negative. So I'm going to say f is concave down for x between this number and what was it, -1. All right, now I need a number between -1 and -0.5. So f3 double prime of what is it? -1 and -0.5, so -0.8. It's positive, so it's concave up for that. -1 to -0.5427. And then -0.5427 to -0.1. So take -0.3. is a negative number, so it's concave down. So that's negative 0.5427 to, what was that number? Negative 0.1084. Okay, and now I've got to remember it's not just where the second derivative is 0 that I need to pay attention to. Those two excluded parts of the domain can also offer a sign change. So I'm going to take this and the second derivative could change signs, might change signs at all of those things, including 2 and 4. Okay, so I need to check between negative 0.1 and 2 and between 2 and 4 and to the right of 4. The second derivative is in purple. I can say, I mean, it's just so clear that the first derivative is concave up between 2 and 4. But I do want to double check that. But so between 0 and 2, the second derivative is positive, and for x greater than 4, the second derivative is positive. So it's concave up for x between negative 0.1084 to 2, and for x greater than 4. And let's double check between 2 and 4. F3 double prime of 3 is a huge positive number. So let's put, it's also a concave up there. And for 2 less than x less than 4, and for x greater than 4. Okay. Then, oops, let's leave that there. And finally, our points of inflection. Basically, we have, we went from concave down to concave up at x equals negative 35.3113. So negative 35.3113 and F3 of that number. Okay, so that's a point of inflection. And where else were we? So here it went from concave up to concave down at negative 4.97777. So there's a point of inflection. It might be, you know, it's kind of good to maybe just put these negative 0.0151. It's a negative. And this would be negative 0.0049. What else? At negative 1, it switches from being concave down to concave up. So -1, f3 of -1 is there. Okay, so at the point -1, 0 is a point of inflection. At -0.54, we went from concave down to concave up to concave down, so that's a point of inflection. -0.5427. So that's another point of inflection, -0.5427 and 0.00001. All right, and we went concave down to concave up at -0.1084. One, two, three, four, five. Okay, so there's all of our points of inflection there. Okay, and again, like if I was to kind of get a real picture of this, we would probably see, you know, the stuff that's happening at this scale. Let me there was a relative, oops, let's get rid of that. So there was a local minimum at y equals -0.01 at x equals -20. So if I was to suss that out, I would want to have, you know, -0.02 to, sorry, no. Y goes from -0.02 to 0, say. And so this kind of gives me a little bit better of a picture. Like I can, in this picture, I can kind of see that local minimum value. And I can also see how I have that concavity change here. Like I can barely see like a little bit of concave downness here and a bit and more concave upness here. And I can see that point of inflection where there's a concave up and then at that green point switches to concave down. And again, I would, you know, probably want to zoom in a little bit more on this and, you know, kind of maybe zoom in to leave the x values alone, but change the y values this time. -0.0002 to positive 0.0002. This gives me a little bit better picture, and I see that concavity change. I was concave down to the left of -1 and concave up to the right, and then at that purple point I changed to concave down, and then I'm concave up for the rest, and then there's the rest of that piece. So I would kind of think there's maybe 3 or 4 different views that really show all of the features of this function. This being one of them, and then using the one where it was, you know, -40 to something, and what was this, -0.02. Okay. So this is another view that kind of shows some features along with that local and global minimum. And then the other feature, I think, or the other window would be probably from x going from like 2 to 4, that window in there, and y was around the 210 mark, so 205 to 220. So I'm going to zoom out so I can see those asymptotes. So there's kind of a picture of that. And you know, maybe I just want to go from 208 to 212. Oops. I don't know. I have no idea. But so there's that little dip that comes up. Oh, maybe I wanted to actually expand more of that. So let's go 100 to 400. There. That kind of shows that picture. Oh, and even going from 0, we can kind of see that picture coming up. Maybe I want to go a little bit higher, 600 or 1600. Interesting. Okay, wonderful. So that gives a little bit better picture of that local minimum. And then you know, maybe we kind of even have a zoomed out picture like that, and that also gives a little bit more of a picture of the end behavior of the function too. Okay, so there's a lot that went into this particular graph. I'm realizing that this was over an hour talking about this one function, and granted, I will say that, you know, I spent a lot of time talking about this, but there was a lot of work that went into finding all of the actual features of this function, that it is not just throwing it in the calculator and being like, oh, that's what the function looks like. We really had to hunt and peck for information for this function. All right, and I believe, yeah, that's all. We've done all of the things on that function. All right, and ending now.